All right, let's take a quick look at using partial fraction decomposition to evaluate an integral. Here's an example. Now, use substitution won't work in this problem. You can trust me or you can try it on your own, but it won't work. So when the denominator is factorable, that's when we might try partial fraction decomposition. First, let's factor the denominator. And now that the denominator is factored, we are going to try to change this fraction into a sum or difference of smaller fractions. We're going to do the decomposition. How are we going to do that? Let's rewrite this as a sum of two fractions like this. All right, now we just need to find out what a and b are. And to do that, we'll set this fraction equal to these two fractions, and then get rid of the denominator. And when we multiply both sides of the equation by the denominator, we will have no more denominators. On the left side, all we're left with is x plus 2. And on the right side, we're left with this sum. Then choose values of x that will make each of these factors cancel out one at a time, starting with x equals -5, which means we'll have 0a plus -5b equals -5 plus 2. So b is 3/5. And when x is 0, we have 2 equals 5a plus 0. All right, so now we can go back to our integral and rewrite this one as this fraction where we know a and we know b. We can rewrite those like the following. Which brings us to something we can easily integrate. And there it is. We've integrated the original integrand using partial fraction decomposition. And now we'll review how that's used in solving the logistic Diffeq. There's the standard Diffeq for logistics, which we should have memorized. And to solve this for p, we'll do separation of variables. Our factors involving p with dp, and factors involving t with dt. In case just a constant, we'll leave it on this side. All right, we're ready to do the integral of both sides. The right side's easy. The left side, we have a factored expression in the denominator, and that's our cue to use partial fraction decomposition. So that fraction can be decomposed into the sum of two fractions, and each denominator is each distinct factor of the original denominator. All right, let's rewrite this equation so that we get rid of the denominators by multiplying both sides by this denominator. All right, then to find a and b in our partial fraction decomposition, we'll choose p-values one at a time, which causes one of these terms to cancel out. So if this blue part was equal to 1, this would be 0, and the a times 0 would be 0, and we could find b. So what value of p lets this fraction be 1 when p is m? And if p is m, then we have 0a and mb. And therefore, b would be 1 over m. All right, now let's force this term to cancel out, and that will happen when p is 0. Let's let p equal 0. And when p is 0, we have 1a plus 0, or just 1a, is equal to 1. All right, we can now change this integral to an integral of a sum or difference of fractions, now that we know a and b. So the integral of the sum is the sum of the integrals, and 1 over m is divided by this difference is the same as 1 over m times this difference, which is m minus p. And remember that m is just a constant, like the number 7 or the number 3. Our only variable is p, and so we can easily differentiate this. Let's go ahead and do it. So remember, our variable is p, and so 1 over some constant minus p's antiderivative is a natural log of m minus p, but then if you're taking the derivative and going backwards, you have to use the chain rule and multiply by -1. we can do that. So let's just change this to subtraction, and then we want this p to be in front. And we can just change the order. You might ask, how are we able to just change the order? Well, think about it. Changing the order in subtraction just changes the sign, but not the absolute value. So the absolute value of -2 is 2. The absolute value of 2 is 2. So since we're taking the absolute value, the order doesn't matter. Let's put our variable out front for convenience moving forward. There were constants in all of these antiderivatives, but they're all combined into this one. Okay, the difference of two logs can be rewritten as a single logarithm of a quotient. Then we can do the inverse of log base e, which is exponential function base e. And we're getting really close to our solution for p. So, and keep in mind that there is actually a p here as well. Anyway, since this right side is equal to this product, e to the c can just be some constant. And since that constant can be positive or negative, we no longer need the absolute value symbols. And then to solve for p, we're going to need to multiply both sides by that denominator. Distribute. Collect our p's on one side. Factor out the p. Divide both sides by that difference. And we're so close to the standard form that we know and love. And to simplify this, we'll multiply by 1 over ce to the kt, so that just completely cancels out with ce to the kt on the top. And when we distribute it to the bottom, we have 1 over ce to the kt minus 1. All right, next, multiply the top and the bottom by a -1. So we have the maximum as a positive all over +1 minus 1 over ce to the kt. And then c can be positive or negative. It can be any constant, so we might as well just rewrite it as c instead of being in the denominator. But e to the kt is in the denominator unless we change the exponent's sign to e to the negative kt. And there we have it. The solution to this logistic differential equation is given by this expression. And recall that this differential equation has many forms. We can change the inside to just maximum minus p. Then that changes the factor out front. Or we could just distribute and get kp minus kp squared over m. So be on the lookout for these. Sometimes you might see something similar that doesn't actually have an equivalent form that is the differential logistic equation, but sometimes you do. And in every case, that is our solution.